Good morning. Any questions, any comments? Welcome back. Superfluid helium. Okay. So I want to talk about superfluid helium, and it is unconventional properties. So let's first remember what helium is. Helium, there have like two isotopes, which we call helium-3 and helium-4. Helium-3 and helium-4. This is by far the most abundant isotope, and this has, for example, helium in both cases has like 2 electrons. If you have 2 electrons, you need to have 2 protons, and in the case of helium-4, you also have 2 neutrons, which is like even number of fermions. Then this entire package is boson because of even number of fermions. So this is boson, bosonic. Whereas here I have like one less nucleon. That means it is fermionic. From a single atomic perspective, this may not be such a big deal, but from a many-body perspective, this makes a huge difference. To highlight the difference, helium-4, for example, is superfluid, or like quantum mechanics emerge in helium-4, it becomes superfluid at 2.17 Kelvin. And historically, this was first observed in 1930s by Kapitsa. You can see 1930s is a long time, so it is actually easy to make a superfluid from helium-4. Whereas helium-3, superfluid, it also has like a superfluid phase, but at 2 millikelvin, about 1,000 times cooler than helium-4. And in terms of years, it took 50 more years to arrive helium-3 superfluidity. This, I think, was then in 1970s by Osterov, Richardson, and Lee. Also, helium-3 you cannot find. For example, today there is like a shortage of helium in the world, especially helium-3, because we are not producing as much nuclear weapons. Now they are trying to go back to nuclear energy for some other reasons. Who knows, there may be more helium-3 in the future, but at the moment we don't have as much. So experiments with this substance is a much harder thing to do. So these are macroscopic quantum phenomena, and they have like superfluid phases. But additionally, there are a couple of things I need to mention, and people, even in this department, have like lifetime research on these areas. One is so-called neutron stars. Neutron stars. Basically, the core of neutron stars are like so high pressure. There's only neutrons, uncharged objects. They just pack together, and in such high pressures and such high densities, they do exactly what helium-3 or helium-4 does. They also go to superfluid phase. But of course, the problem with neutron stars is you cannot put it in a bucket and look at it, right? You have to have like very difficult astronomical observations, and all the evidence for superfluidity in neutron stars are indirect. Another way to say it, it's just a speculation. And that's one reason they are like less exciting, at least for me, because I want to have things on tabletops, and I want to like stir things and look what they do. Another thing is also hydrogen, either in atomic form or molecular form at high pressures, is also predicted to be superfluid. And this is also not, I mean, it is like a very high temperatures. People are also realizing things like this in a lab, but they are like much more limited. But in like a bigger macroscopic scale, they are relevant for, again, if you are interested in astronomy, the core of Jupiter may have the necessary conditions for hydrogen to get superfluid. Again, this is also speculation, right? We cannot go there, put our probes and measure things we measure. So they are not what I am going to be talking about. So these are all what we call examples of quantum fluid. Quantum fluids. And now I want to tell you a little bit more about details of quantum fluids. So let's think about classical and quantum fluids. So we can think about the simplest thing to understand these, and the simplest thing is generally rare earth gases, because they are simple both atomically, and they are also simple as like a system, like a gas. And let's consider rare gas species, two species. One is helium and the other one is neon, and the difference already tells us about the necessary conditions to get quantum fluids. So both of these gases, right, they are like closed shell atoms to lowest order. They don't interact, right? That's why they are rare earth. They don't do anything. They just stay intact. But if you look at microscopics, like at short range, they have like strong repulsion, because anything that's close enough, because of Pauli principle, they have to repel each other. And at long range, these are like composite objects. They are not point charges. There is like a charge distribution, and this charge distribution can have like different modes. One of the modes is like a dipole mode, right? At long range, this dipole-dipole interaction is going to be taking place, and as a result of dipole-dipole interaction is long range van der Waals attraction. Okay. And the typical picture is something like this. Suppose this is the interatomic potential, let's say. So this is V of R, and this is R. Let's start with helium. There's like a very strong short range repulsion and very weak long range attraction, and in between there has to be like a minima. So this is for helium. And to understand the properties of helium, we can compare it with neon. And in the case of neon, we also have a similar thing, but this potential minima is much, much deeper. Okay, this is neon. And unfortunately, we cannot go and like measure microscopic interactions. Right? There is no mechanism like Cavendish experiment. You cannot put it on like a simple thing and see what atoms are doing. So we have to deduce the interatomic potential from other experimental measurements. But a good model interaction is given by so-called Lennard-Jones potential. And it is something like that. It is just a model for us. There's like a depth of potential which is shown with epsilon 0, and there's d to the 12 over r to the 12 minus d to the 6 r to the 6. So d is location or interatomic separation. And epsilon naught is depth. So let me give you the estimates for helium and neon. For helium, epsilon naught is something like, so these are of course not exact figures, but just for us to give like a general idea, this is like 1.03 milli electron volt, and D is about 0.265 nanometers. And for neon, epsilon naught is about 4 times bigger, 394 milli electron volt, whereas D is roughly the same. Neon is a little bigger atom, so it's just slightly bigger, but not significantly bigger. 2.96 nanometers. So from here we can say, like for helium, weaker binding because the potential is like shallower, and lighter mass means stronger zero-point energy, and as a result helium has like a better chance to have like quantum fluids. So I will give a little bit more details in a little bit. So let's try to make some simple estimates. So let's estimate. I also need to have some temperatures here, but yeah, anyways, I'll give you later. Estimate when quantum mechanics should kick in. And since we are making an estimate, we don't have to be very correct. I'll use classical physics, and a good energy scale is kinetic energy, like in a gas, p squared over 2m. This is expectation value of p squared, but I'm not going to write that. And I'm going to compare it to thermal energy, right? There's actually 3 over half and all those factors, but we are making the simplest estimate. So let's not worry about these things. From here, the P should be order of 2m kBT. And a good thing to compare, like quantum mechanics means like a wave phenomena kicks in, and a wave phenomena kicks in if the wavelength is necessary. And the wavelength we can calculate from here is de Broglie wavelength, which is going to be h over p, and it is going to be h over 2m kBT. So right now, temperature is the temperature of your gas, Kb is Boltzmann constant, m is the atomic mass, and you can calculate de Broglie wavelength of each atom at each temperature and then look at them, right? If the wavelength is extremely small, there is no chance you can see any quantum effects. But if it is like comparable to some like experimental parameter, maybe it'll be a quantum fluid. And for neon, which is liquid at 27 Kelvin, right? We can look at the phase diagram and see where it is liquid and where it freezes. Freeze at 24 Kelvin. And M neon is about 20 atomic units. If you put all of these, what you are going to find is de Broglie wavelength is about 0.07 nanometers. But we said atomic potential D, we have just modeled, was about 0.3 nanometers. And we can immediately see D is much bigger than lambda, de Broglie. And it is not as easy to see quantum phenomena in neon. Whereas in helium is I think the only example that doesn't have a solid phase in normal pressures. No matter how low temperature you go, it is always liquid, right? There's no other example as far as I know. And it is liquid. It liquidifies at 4 Kelvin. Like M is 4 atomic units. And if you calculate lambda de Broglie for helium, you are going to find, again, exactly the same formula. I just changed the inputs, 0.4 nanometers. But we can see D was not exactly the same, but order of 0.3 nanometers above I gave. So D is comparable to lambda de Broglie in the case of helium. And that also signals us maybe there is actually a good chance the quantum fluid phase is going to be more likely in helium. So let me also draw you the phase diagrams to see how significantly the quantum mechanics changes the usual, right? The phase diagram is in like water, right? We look at the phase diagrams, like if you want P versus T, P versus T, and let's draw here neon. What you have is typically there is some line and okay, the exact shape depends on the species, and I'm not going to try to be very correct here. Let me just give you like a qualitative picture. So this is solid phase, very low temperature or very high pressures. So this is liquid phase, this is gas. Here is 3 critical points: liquid, gas, and solid coexist at this point, exactly like in water. Water also has this property, and this one is the point where you cross over from liquid to gas, and this is about 20 Kelvin, and this measure here is about, let me call it like 1 megapascal, which is about 10 times atmospheric pressure. But if you do the same measurement to find the phase diagram of helium, what you are going to find is, first, you have something like this, a gas separating the liquid, like this. Maybe I can use the same color. Something like this, and this is about 2 Kelvin. But what is amazing is this is like gas, this is liquid, but there is never like a solid phase, and there is never like a 3 critical point. The solid phase is always like that. So this is solid. And this area is about, if this like under like atmospheric pressures, you don't have a solid phase, but if you go like 100 or 1,000 times atmospheric pressure, which is about 2.5 gigapascal, you have like a solid phase, because you compress the material so much, it has to go there anyways. But what is more amazing is this liquid phase seems to be one phase, but it is actually 2 different phases. There are like 2 different liquids. So this is what we call normal fluid. Sometimes these are called helium-1 or helium-1. And this is helium-2. Let me say without making any mystery, this is normal fluid, this is superfluid. Good. So another thing we need to consider is, right, to understand if things solidify or not, we also can consider 0-point energy estimation. Let's estimate a 0-point energy. For an oscillator, 0-point energy is 3/2 h bar omega naught. you don't have to worry about this 3 over 2. It's, if you want, you can put 1. And omega naught is, there's also again some factors here, not very important. Some spring constant times mass of the helium. And for spring constants, I'm going to use this Lennard-Jones potential and the phenomenological parameters in the Lennard-Jones potential. K is going to be, for example, 1 over 2 d squared v d r squared. If you take the derivatives and put it in the Mirma, what I found is like something like 36 epsilon naught divided by d naught squared. So putting these numbers, E naught 0 point energy is going to be 5 to 10 milli electron volts. And if you change the milli electron volt to Kelvin, right, we can compare it with the temperature scale. This is about 50 to 100 Kelvin. Basically, you are like about a 2 Kelvin temperature, but quantum fluctuations are at the order of 50 Kelvin, right? So there's like a gigantic 0 point energy that's going to prevent solidification. And okay, you can do the same thing with neon. In the case of neon, E naught is also 5 to 10 MeV, but melting point is not 2 Kelvin, but about 24 Kelvin. It's something like 20 to 30 Kelvin. So they are comparable. 24 Kelvin. So in the case of neon, 0 point fluctuations are not strong enough. Now I want to tell you about what happens as you cross along the liquid from here to here. I think that's one of the most studied and one of the most interesting phase transitions. This in the quantum case or in the condensed matter context. And for that, we need to think about specific heat. Let's consider specific heat, CV. If you remember, in the case of Bose gas, calculation of specific heat is like a third year exercise, right? It's like an undergraduate exercise, and we try to do that quickly. What you are going to find is like at high temperatures, this is like this usual Dulong Petit, and oops, it's like a Dulong Petit. There is like a cusp, which we call BEC temperature, and then it's going to decay like that. But in the liquid helium case, that's not what you observe. What you observe is like there's like a TC, which is about 2.4 Kelvin. And what you find is you decrease towards TC. Let me try to be a little bit careful. And then you shoot up, you logarithmically diverge, and then you come back from this divergence and you go like a T cube specific heat, right? Another does anybody remember any other T cube in the specific heat measurements from condensed matter? When you see T cube in a specific heat, what does that signal? Right? That's also not a tricky question, but that's what we start the condensed matter or statistical physics with. Diamond, exactly. What does diamond have?
Low temperature.
T cube. But what is the mechanism for the T cube?
Vibration.
Exactly, phonons, right? So this is also kind of like a phonon, but we are talking about a liquid. That has nothing to do with crystal vibrations or Debye or Einstein mode. We'll see maybe why this T cube is, but this is also different from a Bose-Einstein condensate. We didn't have a T cube Bose-Einstein condensate in our last week derivation. So because this shape, you can see it kind of looks like a Greek letter lambda. And even the experimental output is actually this Greek letter lambda. That's why this is called lambda transition. And this point is called lambda point. So like two different things from a BEC. There is like a T cube low temperature is unlike BEC. And a second thing is the CV around TC, some regular function C of T plus some A plus T minus TC to the power minus alpha when T is bigger than TC, and some other regular function plus A minus T minus TC to the minus alpha, again the same, but the coefficient is different for T less than TC. And this alpha is what we call like sometimes a critical exponent or sometimes universal exponent. Alpha is equal to 0.009, which, so this is experimental results, but this experimental result agrees with so-called XY model. But it is not like a simple-minded mean field calculation. Maybe we can also do the mean field calculation for exponents, and in the future we can compare. But for you to note now is like these are like some scaling or renormalization group. Calculations that give the exponent, and that exponent that comes from that calculation agrees with the experiment to like a great precision. And this is sometimes called XY universality class. So in physics, whether you study quantum or classical systems, whether you study like a traffic jamming or phase transition in a liquid gas, or if you are studying superconductor, magnet, it doesn't matter. You look at the phase transitions and they all show the same universal behavior, right? Doesn't matter. That's what we call universality, and there are a couple of universality classes. One of the most studied is XY universality class, and liquid helium seems to obey that class. And what is that class? Let me tell you a little bit about XY model. Is something like this. We have two-dimensional vectors in three-dimensional space. So this is an x of r, comma, and y of r. If you want, they are like magnets, but these magnets are planar. But these planar little compasses can exist in three-dimensional space. So this is 3D, so this is 2D. Sometimes we write it like cosine theta of r, sine theta of r. And what happens in XY model is you have some bulk, and inside bulk, okay, this is 3D, but I'm going to represent in like 2D. And you have these vectors, and if you are bigger than TC, right? These vectors are in random orientation, like this, no, something like that, something like that. And if you sum all the vectors, the net, if you want magnetization, is 0. Whereas if you go to low temperatures, T less than TC, they have like a spontaneously chosen direction, and they break the symmetry. Maybe I can also expose you to jargon. This is what we call spontaneous symmetry breaking, because here we have rotational symmetry, here we don't. And for each vector, there's like this theta angle is here, and this is n. But here's the question, like liquid helium is like, right? it is not like a magnet. There is no magnetic property of helium. It is like a simple, most compact, most boring atom. There is no structure almost. What does helium have to do with a magnet? Right? What is theta in the helium? What is this? The question is, why theta degree of freedom in helium-4? What does it represent? I mean, today this is not a mystery. We know what it is, right? That's the subject of discourse. But in the early years, this was not so clear. And this theta is the phase of macroscopic wave function. So, macros, exactly like the one taken in the Nobel Prize, right? There is also a macroscopic phase there, and they can create a phase gradient in their system, and they can do this Josephson tunneling, and all those things enable many interesting things in their experiments. But here we are not doing like such a fancy thing. We are just suggesting the presence of a macroscopically occupied giant matter wave. So macroscopic wave function. Typically, we show it like psi 0 of r, exactly like what we did last week. Well, any questions, by the way? Any comments? And so this is, by itself, this is not an observable object, but if you want to, for example, calculate density of particles, so this is, for example, n0 is going to be absolute value, psi 0 squared. If you want to calculate the number of particles, n0 is going to be density times volume, and it is going to be d cube r psi 0 of r squared. But the phase degree of freedom that we are talking about in the XY model comes out if we separate, right? Let's separate the phase. So psi 0, let me not write r, it is r, but let's not clutter the page. So it's going to be some n0 of, let me make it explicit here, r times e to the I theta of r. And this wave function is non-zero below critical value and zero critical temperature and 0 above critical temperature. So, and this theta is ordered. I will tell you what this ordered means over time when t is less than tc. Good. Let me try to introduce just a little bit of terminology that is unique to quantum phenomena, and then I'll finish it there. Any questions? Let's use what we know from quantum mechanics, like quantum mechanics. If we have like a wave function, we can calculate all observables. An interesting observable is, of course, density, and the next interesting thing you can do is current density. And I'll put J0 because I put N0 and psi 0 in all of these, which will be clear in a little bit. And the definition of a current in quantum mechanics is h bar over 2mi psi 0 star del psi minus, this is also psi 0. So this is three-dimensional, and this is psi 0 del psi 0 star. Good. And psi 0 is equal to n0 e to the I theta, then del psi 0 is equal to e to the I theta del and 0. So I am going to hit derivative with this or with this, right? And e to the I, okay, how did I write this? Let me put I in front and 0, e to the I theta del theta. So I just took the gradient, and gradient can act on here or here. And this one brought a factor of I, e to the I, and gradient of del I. So let me do the same thing with psi star. If you take the psi star, this is going to be minus, this is going to be minus, and this is going to be minus. Now I multiply this with here, let me psi 0 star. I'm going to multiply it e to the minus, okay, let me multiply it like n0 e to the minus I theta, because this is psi star. And this one I will multiply with psi 0. And this is n0 e to the I theta. You can see this e to the theta cancels. This one cancels. And to calculate the currents, I take the difference. And from the difference, you can see these terms are identical. They are going to drop out. So if I subtract, okay, this is the last 2 minutes, and then I'll finish it there. J0 is going to be h bar over 2mi. So here 2i, n0 is n0 times gradient of phi, cancel this, cancel i's. At the end, J0 is equal to h bar over m n0 gradient of theta. And if this is the current density, right? Current is density. If you are calculating charge density, there's also a charge minus E here, but this is particle current, N times V, and V is defined from this relation S. So this is V. S is going to be H bar over M gradient of theta. And this is the difference between a normal flow and superfluid flow. So this is superfluid velocity. Sometimes people call superfluid velocity is a potential flow. What this means is superfluid velocity is always gradient of a well-behaved function. I will tell you what well-behaved means maybe in the next course. But the difference from classical physics or classical fluids, we have this property, right? If you take the curl of superfluid, this is h bar over m, curl of gradient. What is this quantity? That's 0 from calculus. As a result, what we say is superflow is irrotational. Okay. Maybe I can just give you the hint here and then continue next time. So this exactly this relation implies that a superfluid, even if you want to rotate, cannot be rotated. But next time we'll see we can actually rotate the superfluids, but for that to happen, we have to have quantized vortices. Good. Any questions? All right. Thank you. Let's continue next time.